This is part 7 of the series Quadrilaterals. In this part, we're going to investigate trapezoids and kites. To start with, let's take a look at what a trapezoid is. A trapezoid is a quadrilateral with exactly one pair of parallel sides. In this figure, this side is parallel to this side based on the parallelism figures, and the parallel sides are called the bases of the trapezoid. Then we have the sides that are not parallel, which are called the legs. So a base is the parallel sides of the trapezoid, and a leg is the non-parallel sides of a trapezoid. The angles that are made by a leg and its adjacent base are called base angles. So the base angles are consecutive angles whose common side is a base. So this angle has a common side with this angle. So these are base angles, and this angle and this angle are base angles. Trapezoid's a pretty simple object, and we're going to investigate more of the properties of trapezoids as we move on. Now let's go to the next shape in the family of trapezoids, and that is the isosceles trapezoid. An isosceles trapezoid is a trapezoid with congruent legs. When these legs become congruent, it adds several new properties to the standard trapezoid, and we're going to investigate all those properties as we move through. So let's move on and try to determine how we can determine if a quadrilateral is a trapezoid. Here we have a trapezoid in the coordinate plane, trapezoid ABCD, and we need to determine if this is a trapezoid. Now we've learned that a trapezoid is a quadrilateral with exactly two parallel sides. So since this side and this side clearly appear not to be parallel, we're going to go with this side and this side. And the way we determine parallelism in the coordinate plane is slope. So let's calculate the slope of this side and the slope of this side. So our first side, AB, we're going to have, so the slope of AB, we're going to have the difference of the y's over the difference of the x's. So 4 minus 3 over 2 minus 0, which gives us 1 over 2. So 1/2. The slope is 1/2. Let's do the same thing with DC. We have 2 minus 0 and 4 minus 0, which is 2/4, which is 1/2. So these slopes are the same. We can see that this one's vertical, so the slope is undefined, and this one's going to have a negative slope, so clearly these two are not parallel. So this is in fact a trapezoid. Now we need to determine if this is an isosceles trapezoid, and the way to determine that is if the legs are congruent. So for this vertical side, AD, that's all we need to do is the ruler postulate. So we're going from 0 to 3. It's even easier than that. It's just AD equals 3 minus 0, which is 3. BC, we have to use the distance formula. So for BC, we'll put our points in 2, 4, 4, 2, and take the difference of our x's, 2 minus 4 is negative 2. Difference of our y's, 4 minus 2, 2. Then we square, add square root. So this is 4 plus 4 square root, and this is the square root of 8, which comes down to 2 square roots of 2. Clearly you can see this is not the same as that, so these are not congruent. Therefore this is not an isosceles trapezoid. In case you're wondering how I got from square root of 8 to 2 square roots of 2, I did the prime factorization of the square root of 8. In other words, we take the prime factors of this number. First prime number is 2. 2 goes into 8 4 times. And then we do the same thing with this number. 2 goes into 4 2 times. When you get to the last number as a prime number, you're done. So these are our prime factors, which means the square root of 8 equals the square root of 2 times 2 times 2. And we know this is the square root of 2 squared times the square root of 2. The square root of 2 squared is just 2. Or the square root of 2 squared is the square root of 4, which still makes this 2 square roots of 2. And that's how you simplify that, just in case you were wondering. Let's go ahead and move on to the next section. At this point, we need to start investigating the properties of isosceles trapezoids. The first primary property is given in the isosceles trapezoid base angles theorem. If a trapezoid is isosceles, then each pair of base angles is congruent, as I'm about to show. So the idea is that this base angle is congruent to this, and this to this. Now let's go ahead and prove this. Now this is a fairly involved proof, so let's get started with it. Here we have an isosceles trapezoid, and we need to prove that angle A is congruent to angle D, and angle B is congruent to angle C. Now, right up front, there isn't enough information yet to prove this. So what we're going to do is we're going to draw an auxiliary segment. And we're going to create the segment from point C to segment AD, and we're going to make it parallel to AB, creating a parallelogram in here. And then once we have that parallelogram, then we're going to go ahead, show that opposite sides are congruent, opposite angles are congruent, and then we'll be able to prove that this angle is congruent to this and this to this. So that's the key, is drawing that auxiliary segment. So let's go ahead and do that. So here's our segment CE, and we write draw CE, segment CE, parallel to segment AB. And the reason for that is the parallel postulate. Given a line and a point not on the line, there's exactly one line through the point parallel to the first line. Now we need to state that ABCE is a parallelogram. Now that we know that ABCE is a parallelogram, we know that AB is parallel to CE by the parallelogram opposite sides theorem. What we've done here is created an isosceles triangle, so we need to show that this triangle is isosceles. And we do that by saying that AB is congruent to CD because of the definition of an isosceles trapezoid, and then by the transitive property of congruent segments, since this is congruent to this and this is congruent to this, this must be congruent to that. So let's go ahead and write those statements down. Now since this is congruent to this, we know that triangle CDE is an isosceles triangle, and therefore its base angles are going to be congruent. We're going to use that to show that these angles are congruent. Now we write triangle CED is isosceles, definition of an isosceles triangle, so we've got that. And we know that angle CED is congruent to angle D by the base angles theorem. Now we know this angle is congruent to that. Since ABCD is a trapezoid, BC is parallel to AD, and therefore AB is a transversal, and so is CD. So the legs are transversals to these parallel lines. That makes angle B supplementary to angle A by the consecutive interior angles theorem, and also angle BCD is supplementary to angle D by the same theorem. So we're going to need that because we're going to use that to show that these angles are going to be congruent. So we're working with angles at this point. So we're going to show that this is supplementary to this and this to this. What we're attempting to do here is to link angle A and angle D. We've said that A is supplementary to B and angle BCD is supplementary to angle D. Since we know that this is a parallelogram, angle B has to be congruent to angle AEC. Because those two are congruent, and these two angles are a linear pair, these two angles are supplementary. So what we have is a condition where we have two angles that are supplementary to the same or congruent angles. And that's what we're going to do to show the linkage between A and D. So the first thing is to state that angle B is congruent to angle AEC, and those angles are congruent by the parallelogram opposite sides theorem. Then we want to state that angle AEC and angle CED are a linear pair, and therefore they're supplementary by the linear pair postulate. So let's do that. And now we come to the finale, where we can say that because angle A is supplementary to angle B, and angle D is congruent to an angle that's supplementary to angle B, angle A must be congruent to angle D by the congruent supplements theorem. And then we can say that because angle B is supplementary to angle A, and angle BCD is supplementary to an angle congruent to angle A, that angle BCD must be congruent to angle B because of the congruent supplements theorem. This is obviously not a basic proof, and it's by no means not the only way to prove this theorem. I would suggest that you go through this again and see if you can follow all the steps, and perhaps you might even be able to suggest an optimization to this proof and come up with one of your own. But in either case, it's a really good mental exercise to work through these things just to solidify these concepts and connections between the theorems and the postulates that we've gone through, as well as the definitions throughout the course. So let's go ahead and move on to the next section.